Hey everyone, in this video I will be covering Learning Target 20, which is all about solving optimization problems. These are always really good problems in this class, kind of like related rates, because it takes what you've learned with derivatives and makes it into like a real world problem. So in this question, we are building a rectangular pen with one side already against a barn, and that means 200 meters of fencing are then used for the other three sides of the pen. We want to maximize the area by giving its dimensions. So part A, we need to draw a diagram which illustrates the situation. And it tells us that x is the length of the rectangular pen and y is the width. So first of all, let's just say we have some barn. Looks like this. And this is a top-down view. Oh my goodness. There we go. Top-down view, where this is a barn. Great illustration, I know. And then we're going to have three more sides of a fence like this, where x is going to be the length and y will be the width. So now we need to identify the objective function as well as the constraint. So our objective, as it says in the question, we want to maximize the area of the pen. Area is going to be equal to the length times the width, but in the context of the problem with its variables, x times y. And our constraint relates to how much fencing we have to use. So we don't need to worry about the fencing on the side of the barn. The barn provides that fencing. So we worry about the other three sides. So we'll have that we have 200 meters of fencing, which is equal to one length x and then two widths y. There we go. Part C, we need to write the objective function as a function of a single variable. So our objective is a equals xy. We need to get it in terms of either x or y. That basically means we need to solve our constraint function for one variable. And I'm going to solve it for x because it's kind of, x is already just on its own, doesn't have a coefficient. So x just equals 200 minus 2y. So from there, I can plug that into my area, my objective function, and I'll get 200 minus 2y times y. And distributing it to make the derivative easier, we'll have 200y minus 2y squared. Finally, find the dimensions of x and y that maximize the area of the pen. So I have an equation, a equals 200y minus 2y squared. I say we need to maximize the area. So maximize, that makes me think of absolute or local maximums of a function. I hope that rings a bell. I did that a couple learning targets ago. So the first thing we need to do with that is take a derivative of the area function in terms of y. So that would be 200 minus 4y. And as always, we set it equal to 0. From there, we set that y equals 50. Easy enough considering we only have one y that we've solved for. So if you did that right and got y equals 50, considering that's the only value that you've actually solved for, you could go ahead and just say, figure that that's your value. We know it's obviously not going to be 0. That's not possible, and there's no upper bound. Or I guess it could be 200, but then you'd have no other fencing from either sides. So you assume it's y equals 50. But what we're going to do is we're just going to do a line chart anyways, because there could be situations where you get multiple values of y or multiple values of x, and you actually find which one is the maximum or which one's the minimum. A little tangent there, but I'll have 50 is the value of y we solve for. This is the y-axis. And what we're going to do is we're going to plug in a value. Let's just say we're going to plug in 10. And here we're going to plug in 100. and to see what sign we get. So 200 minus 4 times 10, that gives us a positive number. So this is increasing. If I plug in 100, I get 200 minus 4 times 100. That's a negative value. So this is decreasing. So that pretty much means that we have some curve of, this is y, and we have some axis. I have something that looks like that, and that occurs at y equals 50. This is a very, very rudimentary sketch. It's just showing that we're increasing, and then at y equals 50, we decrease. That means we have a maximum at y equals 50. This graph right here, really not necessary at all. I'm just showing you what it means to be a maximum. Now that we have the y equals 50, we need to figure out what x is going to be. So when y equals 50, we have an equation for x already. We found that x equals 200 minus 2y. So x is going to be equal to 200 minus 2 times 50. That equals 100. So final answer, we can say that area will be maximized, or max, when x equals 100 meters. I'm going to emphasize the units because in the context of the problem, units are very important. And also y equals 50 meters. And that is our final answer. So this question, like the steps it gives, kind of guides you through it, but we always draw a diagram. Then we need to identify an objective function and a constraint function. And then we'll write the objective as a function of one variable, plug it into we'll write our constraint function. We'll solve for a certain variable and then plug that into the objective to get the objective as a function of a single variable. We'll take the derivative of that and set it equal to 0 to get our points that we're going to test. In this case, we only had 1. In this case, and then we had to make sure it was a maximum, which it was, because we want to maximize the area of the pen. And then we plug it back into our constraint function to get the other variable. And we'll say the area will be max when y equals 100, when x equals 100 and y equals 50. And we'll use units, because units are very important in the context of this problem. So that's it.